student at the Instituto de Astronomía, and also is working on his PhD doing numerical relativity simulation of magnetized binary neutron stars.
Thank you, Daniel. Well, I'm going to talk to you about my PhD project and the advances I have had so far. I chose to give this talk this title, Numerical Relativity Simulations in Magnetized Binary Systems of Neutron Stars, as this is the current scope of my work so far. Well, we know that neutron stars are very important and fascinating objects for relativistic astrophysics. And since the new era of detectors and collaborations have been detecting from them gravitational waves emissions, and also we have been, from the collaboration NICER, having very nice measurements of radii and masses. We have now a very good stage for knowing more assets about the neutron stars. And we also know that they are mostly located in binary systems, as we have seen, for example, for binary millisecond pulsars. For introducing my current work, I first try to model the neutron stars from the simplest case scenario, which is what about if we model our neutron stars as a single static spherical symmetric solution in one dimension, of course, because of the spherical symmetry. So for this, we can solve the Einstein-Euler equations. We prescribe as well conservation equations, so we have the conservation of mass and energy and momentum locally in all the points of our domain. And from this, we get the very famous or so-called Tolman-Oppenheimer-Volkoff equations. In the diagram of the right, I show you the reproduction of a very famous test case, which is namely the polytropic equation of state for a single neutron star in this configuration. And I plot there different quantities related to the hydrodynamics. As we can see there, we have the speed of sound, the resonance mass density, the pressure, and the metric components, all for the coordinate radius. And we can see here, for example, where we find the boundary of our neutron star for this equation. And also, this is a code I developed by myself. And we integrate also in each iteration for knowing as well a quantity known as the tidal deformability of a neutron star. We can regard this parameter, lambda, here as how much we can distort our neutron star from the presence of a companion. So if we study this adimensional parameter lambda, we can find from the comparison with this study by Altiparmak et al., that for our case of this neutron star, again, polytropic equation of state, a radius of 14 kilometers, and a mass of 1.4 solar masses, that our tidal deformability is around 700.86, which is in the fiducial range that this work did. These authors work with around 10 to the 8 equations of state, and also constrained the values, in this case for this plot, of the tidal deformability, getting observations from the LIGO collaboration, and also constraining that the speed of sound squared should be under 1/3. Well, for the scope of my work, I am going to use, or I am using, numerical relativity in its 3+1 decomposition formulation. My intention with this is to evolve the space-time and also its matter-energy components. For this, we have the treatment of the 3+1 decomposition, where we write down the line element for our spacetime in this fashion. And we can regard our spacetime for this formulation as a split of 3D spatial hypersurfaces. And then for different coordinate times, we have different hypersurfaces that are related to the current stage of our evolution. And for the case of my simulations, I focus in 3D simulations. So for this, I need to work in a formulation that is conformal and traceless, known as the Bongarte-Shapiro, Shibata, Nakamura, Ohara, and Kojima formulation, where all these authors have been working on them, and many more. And for this, I evolved these equations throughout my simulations. And for example, if I want to incorporate the hydrodynamics in my simulations, I need to also simultaneously solve these equations here that incorporate the density, the flux, and the energy in each cell of my domain. Okay. For the next case, now I use for these 3D simulations, I use a code called the Einstein Toolkit. This Einstein Toolkit software or project is a compendium of different codes that can work together for targeting or solving out different astrophysical phenomena, of course, with space-time curvature and this 3+1 decomposition. For this, I use the code GR contained within it. And now the same single neutron star I showed you that was solved with my code in 1D, now I evolve it in with this code, but in a 3D case scenario. So as you can see, I'm gonna reproduce again the video. If we have this configuration of a single static TOV, but now in 3D evolution, we can see it remains static and stable as it should. And we can get in the boundaries of the star oscillations as if we were, for example, you can imagine that there is a gradient of the atmosphere and the boundary of the star that when we evolve the space-time and the matter-energy components, we get a perturbation that is located in the surroundings of the star. So from these perturbations, we can get a power spectrum that returns to us the frequencies related to the oscillations of the star. This work was done in the early 2000s, and with my simulation, I got very close, at least less than 2% error for the frequencies these authors got before. Yes, the whole oscillation is, of course, the whole star is oscillating, but these oscillations are mostly located in the center of the star and also in the boundaries of the star. So, because when we put this static solution, we get that we have like this interchange, if you want to see it that way, and thus we get those frequencies.
Well, related to last question, but also what these frequencies represent.
Oh, these are the first one is the fundamental mode of the star, that we know that is from the natural frequency of how the star oscillates in its most fundamental mode. And those three are the first P modes, so-called P modes or pressure modes, that represent how the pressure waves of the star behave with this configuration as it oscillates in a stable solution. Okay. Well, as you may remember from my title, I target magnetic fields and its input in this neutron star's evolution. So for this, I am going to use, again, within the Einstein Toolkit, a code that is called Illinois GRMHD, developed by the people in University of Urbana-Champaign University in Illinois. And pretty much, you may remember that we had these GR hydro equations for evolving, or of course, again, our matter energy components. But in this case, we're going to add as well the evolution of the magnetic fields. So we have a new definition for these equations. And for inputting or making these magnetic fields be located in our domain and within our neutron stars, we make the so-called seeding of these magnetic fields. The most famous in the literature are these two current type of magnetic field ansatz. The first one is if we seed an internal current loop field, so we can have, for example, from this formula, you can see that we have this maxima of, if we have the pressure of the star and we define, for example, a cutoff pressure as, for example, the cutoff density or the cutoff pressure in the atmosphere of our star, we can have in this way the seeding of the magnetic field only within or contained within the star, as you will see in the simulations in the next slides. And of course, we can have the most famous case, or the most renowned case for pulsars, that is the dipolar like field. And well, these authors are the ones that make or that propose this seeding of these magnetic fields and their related parameters. Pretty much we can see here that this parameter AV and this I0 are going to be related to the amplitude of our magnetic field, initial magnetic fields. For the first case, I I seeded magnetic fields within a single neutron star. My idea with this, as you can see from this snapshot, is to seed two current loops within a star artificially. As you see here, I again use the same case I was using before, the polytropic evocation of state. These values for the amplitude, the cutoff pressure, and we have again the polytrope, and we have a parameter called the beta max, which is the ratio of the magnetic pressure against the hydrodynamic or the fluid pressure. So for this case, we have that beta is very big, so we should remain or we should have our star in an unstable configuration, as you can see here from the plots and from the simulation. This is a 3D full simulation done with the Code Einstein toolkit, and we can see that the maximum of the magnetic field remains steady. Yes. In the y-axis, the maxima of the amplitude of the three components, Cartesian components of the magnetic field, y, d, and x. And as you see, they remain steady. Yes, for the initial data, of course, it's fixed, but when we evolve the space-time and the matter-energy components, we see this. Yes. No, yeah, we are evolving everything. We're evolving the star, the matter-energy components, the magnetic fields, because they are all input in the evolution equations. And, well, yes.
Maybe I mentioned.
Yeah.
Magnetic field is consistent with the Einstein equations to satisfy constraints or
let me see. Oh, you mean the constraint equations we evolve in each iteration? Well, so far in the initial data. My guess is yes, but well, what I know that we need to ensure in each stage of the evolution is the divergence-free equation of the Maxwell equations. And for me, that should be contained within the constraint equations, but I'm not sure.
To answer that question,
Mhm.
could you say, where do they obtain those expressions for the magnetic field that you showed in your model?
Yes.
Are those solutions of the constraint equation, or are they put by hand?
Yes, in the limit they are thought to be the solutions, including the boundary conditions for the configuration of these magnetic fields. Because, for example, at least for the case of the dipolar case, we have to solve out for the vector potential, and we have like this component here, the 15/8 constant appearing in this case when we match the boundary conditions. For example, for the dipolar case, we have that in the boundary of the star. We need to match to what we already know from electrodynamics or classical electrodynamics that should happen for a pulsar type dipolar field. So for me, yes. Okay. Well, yeah. For this work, we're targeting to model binary neutron star mergers. For these type of events, as I was mentioning at the beginning of my talk, we have very good observations from the collaboration of LIGO, Virgo, and CAGRA. And we already know that these events comprehend 3 stages, or mainly 3 stages, which is the inspiral. We have these 2 neutron stars inspiraling towards each other, and due to loss of gravitational energy, we have that they merge, and then they form a remnant. That for the case of the binary neutron stars, we can produce in matter of milliseconds a black hole, and it is of interest for us that those configurations that can reproduce what we know occur in the observations we have, for example, in the one of 2017, these short gamma ray burst emissions. The open question would be, what would be the best models or the best space of parameters that can allow us to successfully reproduce this with our simulations? One way to do it is to study different, as I was mentioning to you, different parameters for our space of parameters. We can have different outcomes of the gravitational waveforms. As you can see in the panel at the right, we have different configurations if we modify different parameters from the initial data of our neutron stars. We can have, for instance, the differences if we have equal masses or high mass ratios. Also, if we make that the orbits are rather eccentric or not, if they are precessing or not. And also if we incorporate, for example, in the case of hydrodynamics, viscous fluids. And you can see that the list of authors working in this is huge, and all of them target different variations of these parameters for the simulations. An important comment for the outcome of these mergers of binary neutron stars is that depending on the total mass of the initial binary, we can have different outcomes when we observe at the stages that or at the latter stages that are after the merger. We can have, for example, in the case of a very massive binary, that we have the outcome of a black hole and a torus within a fraction of very few milliseconds. If the binary is maybe not so massive, we can have the formation of what we call a hypermassive neutron star, and then eventually this will collapse to a black hole in its torus. And it is also regarded that we can have also these hypermassive neutron stars forming in later stages supermassive neutron stars that eventually will be stable, or in the case that they remain, as possible solutions for neutron stars. A hypermassive neutron star, as you can see, is just a transition stage between the merger and the formation of a black hole with its torus. And the definition for this sort of object is a mass that, a neutron star that has a mass that is beyond, above the TOV mass, which is the maximum mass in this diagram that we use, namely the mass radius red diagram. And we can have different solutions for different neutron stars if we use, for example, different equations of state to model our neutron stars. I show you here a simulation for a purely hydrodynamic evolution of two equal mass binary neutron star system, and the system is irrotational. It only has the angular orbit velocity of these two masses coalescing and merging. And in this configuration, we use a gamma law equation of state, and we form this so-called hypermassive neutron star. I show you just the first milliseconds after the merger. A good thing when using the Einstein toolkit is that, we use a Cartesian mesh grid, which allows us to recover in a good way the poles, so that, for example, we can post-analyze the ejecta we can have, or outflows, if we locate or if we have our system in the configuration to do so. So for this simulation I showed you, this is the mesh grid at the initial data. The finest spacing of the resolution is around 300 meters for the most nested boxes you can see here close to the centers of the star. This is what we call a medium resolution simulation, because there could be even higher resolution. And I show you here also one of the advantages of using this Cartesian grid, although this is a low medium resolution simulation. This is another case of merger, which is the merger of a black hole with a neutron star. And maybe you cannot see from your positions, but we have like a very dim outflow that we can study here in this D direction. So of course, for better configurations or a better choice of equations of state, and also the input of magnetic fields, we would like to see how these outflows behave and remain steady. And also, of course, the formation of black hole tori. Now, I also performed a study of the evolution of hydrodynamics for these simulations by changing the equation of state. For the case of a single polytrope, I made a simulation very similar to the one I showed you, and we can see that there is a collapse after around 20 milliseconds since the initial data. If we rather choose a gamma law equation of state that affects the region near to the crust of the neutron star, we can see that the evolution of these binary neutron stars can remain in long periods of time, bigger than 100 milliseconds. So for this case, I compare the case for polytrope, this adding of the thermal crust equation of state as a gamma law, which also, I didn't mention it here now, but this allows us to have a configuration that has reheating, and that makes that this hypermassive neutron star will be oscillating for a long period of time. So this is why we have this extension of the evolution. And we can see here that, a very famous test for collapse we perform in numerical relativity is the collapse of the minimum of the lapse function that we can see here is happening for this equation of state that is polytropic. Okay. For the extraction of gravitational waves, we also use the Code-Einstein toolkit, and pretty much the idea is that we expand in multipolar modes the Weyl scalar, C4, which allows us to measure the radiation zone components of these gravitational waves. And this is directly related to a quantity known as the strain. This strain is just the case, I don't know if you have seen the work that the LIGO collaboration does, but we have this deformation or this strain that these 4 long kilometer bars have in underground in the detectors, and these are directly related to what we can obtain from simulations if we make this double integral, and if then we apply some correction factors that we get from each of the detectors. I show here in the first panel the C4 scalar for the fundamental mode L2, M2, and also the strain that we would expect for the 3 detectors of LIGO, Hanford, Livingston, and Virgo. We also know that the modes or the frequency modes associated to these multiples in the configuration for L equals M equals 2 represent the fundamental modes or the fundamental or the most fundamental modes for this gravitational wave strain. As you can see here, I plot all the fundamental modes from the Weyl scalar. Maybe here you cannot see from the range, but this is times 10 to the minus 3 in the amplitude of the C4. And in the other rows, I have 10 to the minus 5. So this is the dominant one. And also from this measurement of the modes, we can get a quantity that is related directly to the gravitational wave frequency. For instance, in this case, I show here, then we're related to this mode L equals M equals 2. And the current work I am doing is seeding these magnetic fields, but now in configurations that are more interesting, or at least for our current scope of the work. And this imposition of the magnetic fields can bring up some difficulties. This is like the later stage of my current work. I wanted to show you here this, some of the things I have been facing lately. And when we perform simulations in the Einstein toolkit, we can have a reduction of all our domain, integration domain, as if we were only evolving, for example, a piece or an octant of our full domain. And this sometimes is done for reducing the computation time, which is very, very high. But we also need, in case we have to use this, we need to be very careful about how we define our magnetic fields, our variables, and all the things related to our simulations. Because if we don't do it properly, we can have ill simulations and the so-called poisoning of the metric. When we iterate and when we integrate these equations, we can have that the spatial metric of our space-time starts to diverge, but just because of numerical reasons, not because of the seeding of the magnetic field of all that. So we need to make these simulations work properly. In this case, what I did is to pass to a 3D full domain space scenario. And as you can see here, these magnetic fields are well behaved. They're in very similar stages of evolution. And right now I am targeting the evolution of binary systems with magnetic fields, as you can see in the panel at the right. And well, I leave you with my final remarks. And for my work in future, I'm going to try to reproduce many results that we can find in the literature, seeding magnetic fields properly, and studying long stability conditions for generating these accretion disks and these outflows I was mentioning before. Thank you.